Hello, everybody. Today I'm going to finish up the local search possibilities. We've had two so far, hill climbing and synthetic annealing, or simulated annealing, pardon me. The third one I mentioned, and now I'll talk more about it. So this is the third of the local search techniques, and it's called genetic algorithm. And just to make sure, the other two are hill climbing and simulated annealing. The problem with genetic algorithm is an attempt to apply evolution to the problem. We start with an initial population chosen at random. Then we evaluate each of the items in the population. Now, I sent you, I believe, for the N queens, a possible way of evaluation. But for this, we might have to modify that a little. We might have to make it 1 over what I gave you as the evaluation. Now, the object is to try to figure out how to do some kind of equivalent of what is called survival of the fittest. And that's difficult. You have to figure out how you're going to do that. What we want is to generate new generations from the new generations, pardon me, I'll put that another way, new generations from the old one. So a new generation from the old one. Then we have to fix it so that the best fit items have more descendants in the next generation. Well, that sounds easier than it is, unfortunately. I've been working for days trying to get my N queens genetic algorithm to work. I finally looked on the web and discovered that I've hit what is a normal problem in the N queens genetic algorithm, and it's difficult to fix. So I'll show you what I've been doing, but I want you to realize that this is not the best technique for the N queens. It's just one that I can show you a little bit what's happening. So I've got a program here. What I'm going to do now is lower this and show you the program. My program at the top, N is the number of queens I have. And in fact, I think N is the number of queens I have. And SGen is the size of each generation. I have an evaluation for the board. I have create my initial generation, mate 2 elements of the generation, producing a child, and create the new generation. Each generation is a board, and as we said before, let me bring this back up. a board is represented as an n tuple, an n element array where an element array B, let's say, where B sub I is the row in the ith column that has a queen on it. We allow only one queen per column. Now that's one way of doing it, but I've just read that it might be better to use a permutation, so that also you get rid of having two queens in the same row. But in any sense, when we're looking at it, however we get it, this is how we represent it. It's the randomness. The problem is, how do you generate one of these? So that's the first. First, we have to get a form for understanding it. Now, as I said, we have an evaluation function. I think I sent you that to do. And it's now time. I need a random number generator, which I do. And then what I do is I create the initial population right here. And then the if is to see if we got a solution. If we got a solution, we don't have to keep going. So if the new generation produced a solution, return 0. You'll notice my create pop 0 is a Boolean, and my create new generation is a Boolean. They return true if they found a perfect solution, and they return false otherwise. Then what I do is I mate the items. Now this was a particular form of mate. There are others possible. This one probably isn't the best. Then I go down here and I create a new generation. And that's just calling the create new generation and trying to get a new one. And the function for creating the new generation says to randomly choose some number and see if the number is good enough for the two items you've chosen to mate. So I picked an R1. I originally had an R2, but I got rid of it. R3 and R4. R3 and R4 pick the two items I'm going to try to mate. R1 gives me a probability that I'm going to compare to the fitness. And if the fitness is less than the, if R1 is greater than the fitness, and for both of them, I'm going to make them. Otherwise, I'm not going to make them. So I'm trying to fix it so that I pick the best. And then I was trying the week, I was trying something else. The mate, I used a very simple method, and it really doesn't do everything I want. What I did was I imitated a true evolutionary type method. For each of the n places on the board, n columns, I randomly chose half of them from one mate and half of them from the other mate. So you'll see here I have a random number, And for all of them, if it's less than or equal to 49, mod 100, I pick it from B1. If it's greater than that, I pick it from B2. Now, it looked like that was a reasonable method, but unfortunately, it leads to a problem. And now I want to talk about the problem. So let me go back to here. Problem with a genetic algorithm solution of n queens is that it reaches a good solution, but not a perfect solution. I tried, I tried something in the neighborhood of 20,000 generations. And all I could do was get a board where there was one possibility of a capture. And no matter what I did, I could not get that generation to generate a board with 0 captures. I thought that it was something wrong that I was doing. I went through it and through it and through it. And it turns out that I should have looked earlier on the web, because this is a known problem of applying the genetic algorithm to the n queens. It reaches a good solution, but not the perfect solution. However, the structure is more useful in other areas, so there is a place for the genetic algorithms. Now, with that, we have finished the idea of searching in most cases. We've got the A* search and the ones that came before that, depth first and best first and best first, and breadth first. And now we have the 3 local searches, which tend to work in one area at a time. The next thing we're going to do is look at a particular kind of search, a specialized one for game playing. How do we pick the next move in a game? Hopefully, I'll have something out for that within a day or two and another homework to work on. So that's where we are right now. Thank you. Goodbye.